All right, we want to thank everyone for joining us today for our webinar on generator switching and transfer switches. Start off with a few announcements. This webinar will be recorded. We will send out a link to the recording and any supplemental files within a few business days of the webinar concluding. This is eligible for CEU PDH credits in the states of Utah and Idaho for engineers and electricians. I will send out my email in the chat for anyone who is interested in that or has any other technical issues. They can always chat with us as well. Your audio will be muted during the webinar. However, you can always ask questions at the question and answer box at the bottom of your screen. We will reserve the questions for the end of the presentation, but feel free to ask them at any time. Other than that, we will go ahead and turn it over to Craig.
All right, thank you everyone. Thanks for joining us. We have, as always, lots of material to cover, and so we're going to get right into it. This particular seminar was actually developed by Generac. I've made slight modifications to it and is sponsored by the Milwaukee School of Engineering. The Milwaukee School of Engineering is a full accredited university. And actually, if you want us to give you credit through their site, you can go on the Generac website and take a test, and then the CEUs are actually valid in all 50 states, as I understand. But we will give you, for those who contact Tyler, we'll give you certificates, and they're good in Utah and Idaho. So we're going to talk about generator switching today, which in the most case, we're talking about transfer switches. Second, there we go. So transfer switches switch between the utility and the generator. I know that's a great revelation. So down here on the lower left, we have our load, and the purpose of a transfer switch is if we lose power on the utility, the transfer switch starts the generator. Then once the generator is up to speed, it switches to the generator. When the utility comes back, it will transfer back to the utility, let the generator cool down, and then we were back at square one. Turn the generator off. And these are some of the transfer switches, as you can see on the right. Transfer switches, this one on the right is looks like more like a 100 amp NEMA 1 switch. The one on the left is a NEMA 3R switch. You can tell those because they have the bolts around the door to make sure that that gasket is fully sealed, and they've got the rain hood and so on. And generally, NEMA 3R switches are not that much more than a NEMA 1 switch, maybe $100 up to $300 or $400. Indoor, you can get NEMA 1 and NEMA 12. You cannot get a NEMA 12 in large sizes. For instance, in a 3,000 amp switch, there's no such thing as a NEMA 12 from any manufacturer because they're sealed and you just have no way to get rid of the heat. But in the smaller sizes, NEMA 12s, sometimes they're just standard and certainly not a lot of money. Outdoors, NEMA 3R, so that's a rain tight enclosure. And then we do have NEMA 4X available, non-corrosive. That's typically a stainless steel enclosure. And those enclosures are a little pricey, but they certainly are available, and they're non-corrosive. Now, this is a switch that is my favorite switch of all time. When I started selling switches in 2003, this was here then and was well established. I don't know when it came out, but probably 1990 or earlier. It's an analog switch. And so for people like me, old timers that like simplicity, this was a good switch. It's been very reliable. It's been used by a number of manufacturers. And over here on the right, you can see this is the controller. The controller has knobs on it, also known as rheostats or potentiometers. And this is one of the things I like about a switch. I am somewhat afraid of anything that has a solid state controller on it because you don't know which buttons to push until you read the manual or train yourself up a little bit on it. This just has 8 rheostats there, and you look at it and it'll say this one's a time delay such and such, and it'll show the seconds, and you can just adjust it to that. You've got some indicating lights on the controller, a test switch so you can test the switch. Transformers are right in here, and these transformers transform, let's assume this is a 480 volt switch, from 480 volts down to, let's say, 24 volts, so that you can put that into the controller and not have to put 480 volts into the controller. And then that way the controller can know what the voltages are on the line. We have our contactor here. That's the main part of the switch. You can see we've got in this particular switch 1 point above and 2 points below. So we have our load connection. We have our emergency connection, which we sometimes also call generator, but it's typically labeled emergency. And then we have our utility connection, which is typically labeled normal. And of course, the UL 1008 sticker. In every class I've done up to this point, I've been saying I love this switch, and one day they're going to get rid of it because it won't meet most engineering specs, because engineers want lots and lots of special functions in the switch, and this is a simple switch, analog. And of course, it's kind of getting long in the tooth, although it is a very, very reliable switch. Well, turns out my fears have been realized, and Generac is now in the process of discontinuing the switch. So analog switches, at least from Generac, are no longer available, and we're all digital, and that's typical of everybody else as well. Generac has a number of switches. They have that GTS. They have a PSTS switch, which is actually an Eaton switch, which they name brand for us. Put our name on there, but it's actually made by Eaton. And then we have 2 or 3 different digital switches that Generac makes. This is their newest switch. This is called the TX transfer switch. So it's kind of typical of the latest, greatest state-of-the-art switch. And this is from the catalog for that switch. And it shows some of the benefits and advantages of the switch, such as surface entrance rating, 100% breakers. This is your controller. If you look at this switch, you say, boy, that looks simpler than the analog switch. Yeah, it actually is. And in most cases, I could sell a Generac digital switch for less money than I could sell a Generac analog switch, because there are more parts, and those potentiometers, a good potentiometer, as you probably know, is not a cheap thing. And so these digital switches for the manufacturers, in addition to having lots of programmability and so on and communications, they actually are a little bit less money to make than an analog switch. So this is a great switch. It's got the highest withstand ratings in the industry right now. And it's got a lot of advantages in terms of modular design and ease of mounting on the wall and ease of wiring and so on and so forth. So in any case, that's kind of representative of the latest and greatest in switches. And we are going to now get into some technical. As you know, we try to keep our seminars very technical and not promotional. So I don't want to spend too much time on promotion. Here's a switch. The red shows that it's energized. And my question here is, what's the size of that transfer switch? Well, if you said 2,000 amps, you are correct. Transfer switches do not have any overcurrent protection in them. And this is one of those little boogeymen, one of those things that can get you, because if you call us and say, hey, I need a generator, here it is. How big is that generator? Oh, let's say 750, 800 kilowatts. It's going to have a 1,200 amp breaker. Sorry. And then you say, do you need a transfer switch? And you say, yeah, give me a transfer switch. Well, what size transfer switch are you going to get? You're going to get a 1,200 amp transfer switch. If we don't ask the question, what size is the utility breaker? Very commonly, I would say at least half the time, the utility breaker that feeds that transfer switch is larger than the breaker in the generator. And that transfer switch needs to accommodate the amps when it's on the generator, but it also needs to accommodate those amps when it's on the utility, And since the overcurrent protection on the utility is 2000 amps, then the transfer switch needs to be 2000 amps. Right here, the dotted line, that is your start circuit. And the standard in the industry is a 2-wire start. And that is pretty simple. When the transfer switch closes a contact, then the battery in the generator goes up 1 wire through that contact back to the generator, and the generator sees that contact is closed, and that tells it to start up and run. And when you want to stop the generator, you simply open that contact. Not all transfer switches operate that way, but that is the industry standard. And so that means if you buy a Generac or a CAT or Cummins or Kohler transfer switch, it will work with Generac, CAT, Cummins, or Kohler generator. They are pretty much compatible. And if you're replacing, let's say, the generator, you typically don't have to replace the transfer switch unless you want to, because they are perfectly compatible. Now, this is the way a lot of installations are. We don't want everything on the generator. By not putting everything on the generator, we can reduce the size of the generator. And so in this particular case, we have a 600 amp breaker feeding loads that will not be backed up by the generator. And then just the critical loads that are backed up by the generator are going through the transfer switch. This is sometimes very difficult to do in an existing installation. We like to do this, but in an existing installation, sometimes the existing wiring simply doesn't permit it. So you can go with multiple transfer switches, or you can just back up the whole building. But this is a good way to go. Unfortunately, these people down here on the 600 amp circuit, as soon as you have your first outage, they're going to be complaining about why they don't have power. I say that from experience. In fact, I sometimes tell the story. We had an outage at Geneva Steel. I was the director of engineering and the general manager of utilities for Geneva Steel, and it cost us $100 million in one night. And so I began putting backup generators around the facility, and I really carefully analyzed everything and did basically this, only backing up the critical loads. Well, the first time we had an outage, I found out that I had missed the most critical load in the entire facility, and that is the CEO's office. And so I learned a little lesson there, and I found out that electricians, being having great ingenuity, every time there was an outage, they would tend to wire more things onto the generator. So it's a good idea to have your generator with a little extra capacity to be able to operate. Generators should typically be loaded to no more than 80%. That's not because the generator can't do more than 80%. That's called engineering margin, and that allows people to wire things to the generator that you didn't want on there. It also accounts for some things that you may not have realized, like the CEO's office. All right, this is the open transition transfer switch. It is a make before break switch. What does that mean? You've got a switch in there, and it's going to disconnect from the utility before it connects to the generator. You're going to have, I'm going to say, approximately 100 millisecond delay there. That differs from switch to switch, but it's a nice round number, and I'm going to use it in this presentation. And so whenever you go from the utility to the generator, you're going to have a 100 millisecond delay. Well, that doesn't really matter, because you had an outage. You probably had a several second delay. The problem comes when you want to transfer back to the utility. And when you want to transfer back to the utility, you're going to have another 100 millisecond delay. Now, most loads will actually ride through that without problems, but you can have computers reset, and you can have controllers, solid state controllers, trip during that transition. So we will talk about more of that in a minute. I'm guessing, because I don't have any statistics, but I'm guessing 95% of the switches that we sell are open transition switches. And the reason for that is they are the least expensive switch. They're the most commonly used. We talked about the momentary outage on transfer. And if you want to maintain the contacts on the switch, do a little maintenance, you are going to have to take an outage in order to de-energize that switch. Let's talk about the sequence of operation of a switch. In this particular case, as you can see, we're energized from the utility. It's in red. And we are going to have 2 transfer switches. Well, how many transfer switches can you put on a single generator? The answer is many as you want. We did a hospital recently where we had 17 transfer switches, and then we also had an additional 18th transfer switch that was on the fire pump. Those transfer switches are typically supplied by the fire pump manufacturer. So in this particular example, we have 2 switches. The 2-wire start works just great. You just parallel the wires. So if either one of those switches closes its contact, then it will start the generator. So you may have one switch that for some reason loses power and the other switch doesn't. That generator will still start. So now we're going to have an outage on the utility. The next thing that happens is there is a line interrupt delay. On that analog switch, that's one of those little potentiometers on there. On a digital switch, of course, this is a programmed value. So in this case, you are going to delay for some period of time. If you're in an emergency situation where you have to have the generator online in 10 seconds or less, that delay is going to be short. In some other cases, they may want a half an hour delay because they don't need the generator right away. Let's say they have a tank of water that just needs to be filled. So after that line interrupt delay, then the transfer switch is going to close that contact and it's going to start the generator. The next thing is the transfer switches are going to verify rated output, rated voltage, rated frequency on the generator, and then they are going to go ahead and transfer to the generator and your facility will be powered up. Now, after a certain amount of time, the utility comes back. In storms and things, it's very common for the utility to come back and then go out in a second, or come back and go out in 10 seconds. And so you don't want to transfer back to the utility right away in general. So you're going to have a return to utility timer. And that's another one of those little knobs there, or a variable in your digital switches. So you wait until you feel like the utility is back to stay. Then you go ahead and transfer back to the utility. You keep the switch closed to allow the generator to cool down. Generators will last longer if you allow them 5 or 10 minutes to cool down, and then you go ahead and open the switch and stop the generator. So very straightforward operation. Now let's talk about some different kinds of transfer switch. This is called a bypass isolation switch, or BIS. And down here is a diagram of the bypass isolation switch. And you can see that in this particular diagram, you have a switch that, your automatic switch is right here, and the automatic switch goes to the load. But then you have some bypass switches. So let's say you're in a hospital emergency room, you need to do some maintenance on that switch. You can go in there and you can close this manual switch to the utility. And then you can actually, in this case, you can see it's a draw out switch. You can pull that switch right out onto the floor and do your maintenance, but the facility continues to get power. These are made in a number of configurations. This is a Generac switch in which the way they make it is actually to have 2 completely separate automatic transfer switches, and both of those are draw out, so you can draw out either one in order to do maintenance. Why do you want to use a bypass isolation switch? Because you're on a load that you never ever want to de-energize. Hospital emergency rooms, hospital operating rooms, and maybe even data centers. All of your switches in a hospital do not need to be bypass isolation, just the critical ones. And bypass isolation switches cost, this says 3 times as much as a normal switch. I would say 3 to 5 times as much as a normal switch. So you can see bypass isolation switches, they're more complicated, which means you need to have a little more training for the service people, and they are a little pricey. But if you simply cannot allow for an outage, then you're going to need to go with that bypass isolation switch. Next thing is a service entrance switch. I told you that switches do not have a circuit breaker in them. They do not have a fuse in them. They do not have overcurrent protection. And that means that if you are putting a transfer switch, let's say on a pump station, and you just have a small building and you're putting the transfer switch in there, you have to have a service entrance disconnect. And so you put in the service entrance disconnect, you wire from the service entrance disconnect to the transfer switch, then you wire from the transfer switch to the load. Well, you might say, why not combine the service entrance transfer switch, the service entrance breaker, or the service entrance fuse switch, typically a breaker, with the transfer switch in one box. That way you can mount one box on the wall and all these connections are made at the factory. Well, in fact, that's a very common type of switch. We call it a service entrance rated switch. And the service entrance rated switch can be built in two ways. You can either have a contactor-based switch with a circuit breaker that is on the utility side only. We don't put that circuit breaker on the generator side because typically the generator has its own circuit breaker. So you just have one circuit breaker that's on the utility side. Or you can actually build the switch from circuit breakers. We'll show you that in a few minutes. A service entrance switch is actually less expensive than going in and buying a switch and a service entrance breaker. And then once you add in all the labor and the cabling and the connections and everything, it's kind of a no-brainer. So wherever that is a convenience, makes a lot of sense to go with a service entrance rated transfer switch. I will mention as we get further, also service entrance rated transfer switches may be switches that you want to use to get the withstand rating that you need. And in that case, it's not so much a withstand rating. They actually will trip because they're made with circuit breakers. But that's the only way you can get a 65 kA switch is with circuit breakers. This is a switch with circuit breakers. And so in that case, because they're circuit breakers, if you put in 65 kA circuit breakers, that switch is going to have a 65 kA rating. Now, it's not really a withstand rating because that's going to trip if you get a fault like that. But that's another way to do a service entrance rating, and it's a way to get 65 kA on small switches. That switch looks a lot like one I did up at Hill Air Force Base, and we realized that it needed to be service entrance rated. And so we looked around, couldn't find a sticker, and called the manufacturer and said, hey, we need this switch to be service entrance rated. And they said, that'll be fine. Order a service entrance rated switch from us and switch the two out. We said, but it's already got breakers. It should be fine. Well, it was missing one critical item, and that's called the UL sticker. And so we actually had to buy a new switch in order to get the UL sticker. So not only in a service entrance switch do you need to have the appropriate equipment there, you need the sticker. So you need to make sure that it is ordered as a service entrance switch. Service entrance switches are very good for retrofitting whole building applications. They're good for small buildings. They're good for old distribution equipment to bring everything up to code. In many cases, you have power going into a building and the service entrance disconnects are actually in the building. And this is a good way to put a service entrance switch outside so that it's easy for the fire department and so on to disable the power in the instance of a fire. The other thing that you can do, which is fairly common, is let's say the engineer designs the building, puts in a 2000 amp service, and you look at that service and you look at your utility bill, and the highest current that you have ever had is 400 amps. Well, you can go in there, instead of putting in a 2000 amp transfer switch and all the gear, you can actually put in a 600 or an 800 amp service entrance switch, even though that's 2000 amp gear, as long as you know you're not going to need that power. And that can be a way to save money and to make things much more straightforward. Now let's talk about a closed transition switch. So this is a closed transition switch. It is a make before break switch. Now, in order to do that, as you can guess, it requires two mechanisms. Because let's say that you're operating on the generator and you want to go back to the utility, you close the breaker or the contactor between the utility and the load. And at that moment, you actually have the utility, the generator, and the load all paralleled, all tied together. Typically, that's a no, 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 no. However, we're allowed to do that on a closed transition switch because the maximum overlap is less than 100 milliseconds. So we close on the utility and then we quickly open the generator. And by doing that, there's no outage. And you can see down at the bottom, step one, the utility and generator must be in phase. We will talk about how that works in a moment. And then step two is you close the switch to, in our example, to the utility, but it could be in either direction. And then you open the switch to the generator. This way, we don't have the retransfer outage. And after your outage, when you're going back to the utility, you're not going to have that 100 millisecond outage in which you could have computers reset or a solid state devices trip. So if you do that, you need to have protective considerations. Due to time, I can't really get into that in detail. But obviously, if you can't have more than 100 milliseconds with all three of those tied together, or you could have some serious problems, and you typically may have a protective timer that trips a breaker if they stay connected for too long. What's the benefit of a closed transition switch? Well, one is you can exercise with load. You can go back and forth between the generator and the utility, and nobody will know the difference because they're closed transition. Other benefits could be storm mitigation. Sometimes airports, if they have a storm coming in, like to go to their standby generators so that they can anticipate an outage and not have that outage during the storm. And it reduces the power outages on retransfer. And if you have heavily inductive loads, which we will talk about shortly, then this can be helpful. I feel that if more people considered a closed transition switch, more people would be buying closed transition switches. I think most people, when they buy a transfer switch, say, hey, I just need a transfer switch. And so we quote a transfer switch, and the least costly is going to be an open transition switch. But if they realize that they had this option, they might very well want to consider going to a closed transition switch. Now, closed transition switches are more expensive. And so there is a cost to this feature. But we sold a switch to a water company a little while ago, and I said, hey, I would use a closed transition switch so you don't have that retransfer. But we gave them a quote on both an open transition and a closed transition, and they decided they didn't want to spend the money. And so they bought the open transition. And then a while after, when they started having outages, they came back and said, hey, how come there's a outage when we go back to the utility? It's because you didn't buy the closed transition switch. So something to think about. Now let's talk about application considerations. We're going to start with an in-phase versus a time delay neutral switch. We'll start with the time delay neutral because that's the easiest one. And the time delay neutral switch has a neutral position. Now, all switches do not have a neutral position. And so if you want a delay in neutral or a time delay neutral switch, you must buy the switch that way because it has to have a neutral position. So if you're going back from the generator to the utility, you go to the neutral position, you hold in that neutral position for several seconds, generally at least 4 seconds, and then you go ahead and go to the utility. Now, why would you want to do that? Well, let's see, that slide's coming up in just a moment. Now, this is an in-phase transfer switch. Typically, in-phase transfer switches do not have a neutral position. They have to be in either the generator or emergency position, or in the utility or the normal position. So if you're going to transfer quickly from the generator to the utility, or vice versa, you better make sure those two are in phase. Otherwise, you can do some extensive damage. And so how are you going to do that? Well, one way to do that would be to put controls on the generator and synchronize with the utility, and hold the generator in synchronism with the utility, and then transfer. Yeah, you could do that, but it's very expensive and very complicated. And so the better way to do it, and the way all of these switches actually do it, is just wait until they're in phase. So here you go. You can see the yellow generator power and the utility power. We just wait. The switch simply watches, and whenever those two happen to be in phase, then it quickly switches. Now that's why we recommend setting your generator not at 60 hertz. We would generally recommend that you put it at maybe 60.1 hertz or 59.9 hertz. Let's assume that you're at 60.1 hertz on the generator. That means the difference between the generator frequency and the utility frequency is 1/10 of 1 hertz. And that means that every 10 seconds, the utility and the generator are going to be in phase. And so by waiting, we know that we will be able to switch within 10 seconds because they will be in phase. Now, if you don't do this and you set the generator for 60 hertz, generally these phases bounce around and this switch works anyway. But it is possible that you could have some serious delay time if everything were stable and you were out of phase and both of them were at 60 hertz. So in-phase transfers are the standard switch. And if you say, I just want to switch, you're typically going to get an in-phase transfer switch with a open transition. Now, why would you use a time delay neutral? Well, sometimes UPSs with filter capacitors can have a problem, but mostly we just do this for large motors. So what happens is you disconnect from, let's say, from the generator, and at that point your motor is coasting, and the phase of the motor will instantly change by the phase angle of the voltage inside the motor. But then the motor begins to slow down, and you say, yeah, but it's only 100 milliseconds. Well, in 100 milliseconds, that motor can be significantly out of phase with the utility. And so then you transfer back, you're transferring those big motors out of phase, and you kind of slam that motor because they're out of phase. They're not out of phase generally by a large amount, but it is enough that it can cause problems. And so if it's a 5 or 10 horsepower motor, I don't really care about it too much because they're fine with that. But as you get into larger motors, you can actually cause extensive damage to the motor. And so on larger motors, then we always want to recommend a delay and neutral switch. Of course, this means you're going to have an outage that's typically 3 or 4 seconds. As you can see there, you want to wait for that residual voltage to decay before you transfer the switch back. And so that's the disadvantage, is you have that outage. But you certainly don't want to damage large motors. And so that's really the big reason to use a delay and neutral switch. Typically, a delay and neutral switch is going to be a little bit more expensive than an in-phase transfer because you've got to have that neutral position. Okay, here is one of the controllers that Generac has. Most controllers are going digital, and the controller offers control monitoring protection. Once you get a microprocessor in there, then of course the sky's the limit on all kinds of features that you can put into there. It's got alarms and event logs. It can have communications. It can have remote annunciators and so on. So this obviously is the way the market has gone. And typically this is the type of switch you're going to get. And now that they're discontinuing my favorite old person analog switch, this is pretty much what you're going to get from anyone. The switching device could be either a contactor or a molded case circuit breaker. most people would prefer a contactor. And the reason for that is that contactors are really made for switching. When you're starting a motor, you typically don't use a circuit breaker. Circuit breakers are not made for frequent and repetitive switching. Circuit breakers are made for protection of circuits. They're made for overload protection, short circuit protection, and they can have a lot of operations. So I'm not saying that a molded case circuit breaker or an insulated case circuit breaker based switch is not a reliable switch. It is, but generally I like to go with a contactor based switch, and most people do, and I will only go to a molded case switch if there's a reason why the contactors do not work. The biggest reason, I shouldn't say that, not generally the biggest reason, but one of the biggest reasons is contactor switches. Let's say in 100 amps, you can't get them with a 65 Ka withstand. So if you want to go to a molded case circuit breaker, you can get that higher withstand. And if you insist on a 65 Ka rating on your switch, we're going to provide you molded case. Another reason to go with molded case is that it's less expensive to get a switch with 2 molded case breakers than it is with a transfer switch made of contactors and then an additional molded case breaker for your service entrance. And so sometimes for cost reasons, we will use these on service entrance based switches. So again, I prefer the contactor based switch, but I don't argue too hard to go to, if there's a good reason to go to a molded case switch, I don't have any problem doing that. Now let's talk about fault current ratings. Here is a situation which we have a fault current, and I am not going to talk about this extensively because we have very limited time today. But I've mentioned it a few times. When Westinghouse invented the high interrupting circuit breaker, they decided that they wanted to allow you to use up to a 2500 kVA transformer at 480 volts. And so they looked at the short circuit current of a transformer like that with some motor contribution and settled on 65 Ka because that would let you use a 2500 kVA transformer. Prior to that, engineers were using no more than a 1500 kVA transformer. And so this was a great thing for system design. And so you'll notice that since other manufacturers followed Westinghouse's lead, 65 Ka is a very common rating for molded case circuit breakers. And engineers have gotten to where they would just like to specify everything 65 Ka. I don't blame them. I agree with it. I like it. The problem is no one in the industry makes a circuit breaker based, a contactor based switch with a 65 Ka rating. Here's the Generac TX transfer switch. Right now, the Generac has the highest withstand ratings in the industry, and you'll notice they don't get to 65 Ka so very quickly. Now, you can get with a specific breaker rating, a 65 Ka rating on a 300 amp switch, but many people prefer to go with this 3-cycle rating because they don't know what circuit breaker is going to be upstream of the switch. And typically you're going to have to go to about an 800 amp switch in order to get a 65 Ka rating. And so if you say, I want 65 Ka and I got a 100 amp switch, what options do I have? Well, I could put a fuse in there, but generally that's not the best way to do things. And so I either have to use an 800 amp switch in place of the 100 amp. And you're going to say, why did you sell me an 800 amp switch? I only wanted a 100. Well, because we needed that 65 Ka rating. The other way of doing it is to sell you a circuit breaker based, generally service entrance switch. And that's fine. And I have no problem doing that if that's what you really need is a 65 Ka rating. Now, the last thing we're going to talk about is separately derived versus non-separately derived. And this is, to me, the most interesting part, but we're going to have to go through it very quickly. I was told by my mentor when I first got into this business that bringing up grounding with an engineer is the same thing as throwing a mouse on the table at a ladies' luncheon. And so grounding is always a difficult thing and something that is many times debated. This is just your standard background. Your grounding conductor is the green wire, and that is the wire that actually goes to dirt, or what the Europeans would call earth. Then you have a grounded conductor, and typically as we talk about this, the neutral is the grounded conductor, because we're going to connect a neutral to ground bond per National Electrical Code in order to ground that neutral. It is possible to ground phases and other things, but that's beyond the scope of this particular presentation. So we are going to talk about 3-pole switches and 4-pole switches, and we typically use on a 3-phase system. A non-separately derived system would require a 3-pole switch. A separately derived system would require a 4-pole switch. So what does that really mean? Well, I had some problems with this because they actually changed the definition of separately derived. It used to be if you had a generator and a transformer, they were separately derived. They were 2 separate sources of power. Well, then they changed the definitions in the code, and the definitions say that if you have, let's say, your 3 phases are separately derived, so they either come from the transformer or they come from the generator, depending upon which position the transfer switch is in. But the neutral, if the neutral is not switched, then that neutral is the same conductor between the transformer and the generator, and therefore, according to the current version of the code, this is classified as a non-separately derived switch, and it is non-separately derived because the neutral is not separately derived. If we switch the neutral, then it would become a separately derived switch. So we generally like to use a 3-pole switch because we don't really like switching the neutral. It's better not to switch the neutral. It's best to have that neutral just under the lugs. But it may be that there are reasons why we have to switch the neutral. Well, advantages of 3-pole switches are better neutral bonding, no ground plane required at the generator, simpler system, and lower cost. And that would be a non-separately derived system. Let's take a look at this. This is a separately derived system. And as you can see, this would have 3 switches on the phases and an additional switch on the neutral. And that way it is called a 4-pole switch. Now let's go back here. You'll notice that the neutral to ground bond, you can have one and only one neutral to ground bond according to code. And since this is all one wire, the neutral to ground bond occurs at the service entrance of the utility. And the way the generator is grounded, and I'm not talking about the frame of the generator, I'm talking about the neutral to ground bond. The frame has to be grounded as well, but that's not shown on this drawing. We're going to come from the star point or the neutral of the generator, go to the neutral bus bar of the transfer switch, and the neutral to ground bond for the generator is actually at the service entrance of the building. You may not ground the generator, because if you ground the generator, you now have 2 neutral to ground bonds and you are violating code. In this case, we must ground the generator because the neutral is switched. And so when you switch to the generator, we no longer are connected to the building neutral to ground, and therefore we must connect the ground at the generator. This is difficult, and I always encourage engineers to specify on their drawings, connect neutral to ground bond at the generator, or do not connect the neutral to ground bond at the generator, because it's difficult for an electrician who is not steeped in generator installations to understand this. And it is very common to see generators that are improperly connected. All right, I want to show you a couple of examples, and let's go back here. There are 3 reasons to use a 4-pole switch in general. And that is, number 1, Number one is you have more than one transfer switch and you have ground fault protection on the utility. Number two, you have high sensitivity ground fault on the generator. Or number three, there are more than one building. Now let's dispense with number three. If you have more than one building, that means more than one service entrance, and each of those service entrances is going to have its own neutral to ground bond. So it's clear you can't just tie all that together. And so you're going to have to switch the neutral in the transfer switches in order to keep only one neutral to ground bond at any given time on the system. So if you have more than one utility service entrance, and I'm saying more than one building, but it really comes down to service entrances. If you have more than one, you need to have multiple transfer switches, and they need to be 4 poles so you can isolate that neutral. Now here's one in which we have multiple transfer switches, and let's assume that we have a 3-pole transfer switch. Now down here on ATS, you can see the red arrows. We are just supplying a normal load. Let's say it's lighting, and that lighting is 277 volts. And let's assume we have a 3-pole switch. So there is no switch here, and there is no switch here. The neutral is just a bus bar. This obviously on the diagram, it shows a switch, but I want you to pretend like there's only a bus bar there. So we come out of the generator, we go through the phase A, B, C, or let's say just phase A to a single light. We go down, we go through the light, and we come back on the neutral. When we get here, this is just a bus bar because we're using a 3-pole switch. How does that current get back to the generator? Well, it could go this way, or it could go this way through there, that feeder, up here through the feeder number 1 transfer switch, then back to the generator. Well, which way is the current going to go? Well, you know the answer. It's going to go both ways. And when it goes both ways, as it goes through here, through that feeder with ground fault protection, it's going to trip the ground fault protection because that's no longer balanced. Then it's going to go up and around and through here, and it's going to trip that ground fault protection. So here we are in a situation in which we have no fault. We simply have phase to neutral loads. And as soon as we switch to the generator, all of the breakers on the utility side starts tripping. And especially if this is in the middle of the night and you're the electrician here, this could give you the idea that you got some gremlins running around. So we have to use a 4-pole switch. And by using 4-pole switch, it forces that current to go back to the generator the way it's supposed to, and everything works just fine. Here's another situation. So remember, our first situation was multiple buildings. Second situation we've talked about was multiple transfer switches. Now let's talk about ground fault on the generator. So this is a generator. It has 0 sequence ground fault. And let's say, again, we have a 3-pole transfer switch. So this is just a neutral bus bar. And because of that, we do not have this ground on the generator because it's a 3-pole switch. Now, in this case, we have an actual fault. So it comes out, it goes through the transfer switch, it goes to ground. And then how does it get back? Well, the only neutral to ground is over here at the service. So it comes up through the service, it goes through the utility breaker, again, tripping the utility breaker, and then it goes through back through the generator. So you can see, or the generator 0 sequence sensing. So it came out from the phase, it goes back on the neutral. The generator cannot see that fault. And therefore, to the generator, there is no fault. But all the utility breakers trip. And so in this case, again, this is high sensitivity ground fault on the generator. And in an instance like this, you must have a 4-pole switch and you must have a ground at the generator, and then everything will work fine. Now you can sit there at your desk and trace currents around and try to decide whether you should use a 3-pole or a 4-pole switch, but why not just go with industry standards and ask yourself these 3 questions. Do I have more than one transfer switch and ground fault protection on the utility? If the answer is yes, you have to use a 4-pole switch. If you have good sensitivity, or in other words, 0 sequence ground fault on the generator, and notice this is not ground fault protection, This is ground fault indication. We tend not to trip on ground fault because why would you trip an emergency generator? If you have that zero sequence, you must use a 4-pole switch. And if you have multiple buildings, you must use a 4-pole switch. If any of those questions is true, you use the 4-pole switch. If none of the questions is true, you would go ahead and use a 3-pole switch. Now, the other thing that makes it slightly more complicated is what if you don't have a neutral? Well, if you don't have a neutral, you're obviously going to have to use a 3-pole switch and ground the neutral at the generator. Even though you don't really have a neutral, you're grounding that star point at the generator. If you have a system with some 3-pole switches and some 4-pole switches, then you're going to have to make that a separately derived system and use 3-pole switches where you have no neutral, 4-pole switches where there is a neutral, and you're going to want to ground the generator. And hopefully you can understand the idea behind that. So this is a little final backup. Wastewater treatment plant, what would you use? I would really like to use a closed transition switch there to prevent outages. Office building, generally a standard in-phase open transition switch. Data center, generally they're going to tell you what they like, but often just a standard open transition switch is fine, but sometimes they want to go with closed transition or even bypass isolation. Airport is where they may want to go with a closed transition switch in order to switch to the generator during a storm. Hospital critical loads, you must use a bypass isolation switch. If you want to retrofit a whole facility, many times you don't need to, but a service entrance switch sometimes will be easier and quicker and cheaper. And we are not talking about base loading and peak shaving in this particular presentation. That's kind of a whole deal all by itself. So that is the end of our presentation. And I will open this up for questions and or comments.
Great, Craig. We had a couple questions come in. Feel free, everyone, to continue submitting questions. The first one we had is you had mentioned there was a problem in a specific instance of someone losing power when they transition back to utility power, and the person who submitted this question wanted to clarify if that was because they didn't install the closed transition switch or something else.
Yeah, that's because you don't have a closed transition switch, and that's the whole reason you use a closed transition switch is when you go back from the generator to the utility, you have no outage. And if you want to exercise and go back and forth between the generator and the utility, there's no outage. If you have an open transition switch, then obviously it's a break before make, and so you're going to open the generator before you close to the utility, and that happens very quickly, generally less than 100 milliseconds, but that can cause problems in a facility, and so that is that's why you use a closed transition switch.
Great. The next question is, so just to be clear, a make before break scenario will only occur after synchronization between the generator and utility.
That is 100% true. I think that comment is very well stated. If you are going to have a make before break, you must be synchronized. And again, we don't actively synchronize. We just wait for the two to be in phase. Now, you also need to be synchronized if you're going to use a in-phase transfer switch, because they transfer so quickly that you still kind of need to be synchronized. And again, we just wait.
Okay, the next question is, for in-phase transfer, if break before make, why wait?
In-phase transfer, if say that again.
They said for in-phase transfer, if break before make, why wait?
All right, I'm not sure that I completely understand that question, but I think the issue is, I told you we need to wait until they are in phase. The idea is if you have a motor and you open up on the utility and you then close into, or open up on the generator, either way actually, and then you close into the utility, the motor has residual voltage. It takes time for that to decay. And if you do that in 100 milliseconds, the voltage on the motor is going to be 90, 80, 90% of its rated voltage. And so then if you come in out of phase, that you're going to shock that motor. You can break shafts, you can tear the motor apart, you can do extensive damage. So you never ever want to switch between a generator and a utility unless, number one, they are in phase, or number two, you wait at least 4 seconds for the residual voltage on those motors to decay to, I would say, less than 5% voltage, and that protects the motors from an out-of-phase transfer.
Okay, the next question is, could you explain more on zero sequence generator?
Yeah, that's probably zero sequence ground fault. Zero sequence ground fault is a very, very sensitive type of ground fault. For instance, if you get a circuit breaker and it's got ground fault built into it, they take the 3 current transformers in the circuit breaker and they simply sum them together, and that's your ground fault current. The problem is they're not really linear, and so they can't really be very sensitive. And many times you buy a circuit breaker with ground fault in it, you're setting the ground fault to like 80 or 90% of the trip value of the circuit breaker. A zero sequence has very, very sensitive ground fault. You can trip down around 2 or 3 amps. But the only way to do that is you take all your phases and your neutral through a CT. And if you take all the phases and the neutral through a CT, then the flux, the magnetic flux, balances. And if you see any current, any net current, in other words, the current in all 3 phases plus the neutral should always be 0. And if it's not 0, then that current had to come back through ground someplace. So by doing that, it sums by the flux in the current transformer, and you can sense very, very low values of ground fault and trip that way. This, by the way, is the way your ground fault circuit interrupter works in your house, on your receptacles. But you might want to look up zero sequence and get a little bit more lengthy explanation than I've given you. But this is very, very well accepted in the industry, and engineers use these zero sequence relays all the time. Like on every medium voltage motor, I would use a zero sequence ground sensor. We don't see them very often in generators, but sometimes an engineer wants them there.
All right, we have another question here. What are the implications for NGR applications?
Okay, that's a wonderful question. And in order to get into that in the detail that I would like, I don't really have the time, but let me just mention this. NGR is neutral ground resistor, and I am going to assume that what we're talking about is a high resistance grounding system. So in a high resistance grounding system, you have a ground resistor in your neutral to ground bond. And that ground resistor will typically limit current to 3 to 5 amps. Again, I'm talking about a high resistance ground. There are other types of neutral ground resistors that I won't get into, but let me just look at that particular system. And so that's really nice. It's a lot safer system. And the real advantage that we have used, or that we have seen in that system, is that it allows you to continue operating even if you have a ground fault. Because when you have a ground fault, it limits the current from phase to ground to, let's say, 3, 4, 5 amps, something like that. And you can keep running. And then you take out a meter with a big old CT on it, and you go around and you can do pulsing and find the ground fault, and you can eliminate the ground fault all while you're running. Now at Geneva Steel, which is one of my experiences, I have neutral ground resistors all over the facility, because an outage there is $100,000 an hour for us. We can't afford to be out. And so we don't want some small phase to ground fault to take us out. So we have those high resistance grounding systems all over the facility, and I'm a big fan of them. Now, Can you use a generator with a high resistance grounding scheme? Yeah, absolutely you can. There's no problem. And there's various ways to do that, but typically what I'm going to do is I'm going to use one system with a neutral to ground resistor on the utility, and I'm going to use another one on the generator. In fact, you can even do this on modular systems. We have some systems out at industrial plants where we have two generators and a utility and a high resistance grounding scheme. And that gets a little bit more complicated, but certainly easy to do. And so there's no problem using a neutral ground resistor with a standby generator. You can still use an in-phase transfer switch or a closed transition transfer switch. They work just fine. They will still synchronize. But you do need to make sure you have a ground on the generator and a ground on your utility. And typically, that is done by using two ground systems, two neutral ground resistors, one on the generator and one on the utility.
All right, please explain the difference between open in-phase and delayed transition functionality. What other ATS are there?
Well, this is open transition and closed transition. Is that what it said? Or I'm sorry, try that again.
It said open in-phase and delayed transition.
Okay, so with an open in-phase switch, then what we're doing is we're waiting for the generator and the utility to be in phase, and they will be in phase. You just need to sit and wait, and eventually they're going to be in phase, and then you hurry and switch. And on a in-phase transfer switch, there's no neutral position, so you simply switch very quickly. You open up the generator and close into the utility, and there will be less than 100 millisecond outage. On a time delay neutral switch, we use that as with large motors. There you have to have a neutral, a little bit more expensive switch. So you're going to open the generator, you're going to go to a neutral position in which the load is not connected to either the generator or the utility. You're going to wait, in my mind, at least 4 seconds, and then go ahead and finish the transfer. And in that 4 second, you're allowing the residual voltage on the motors to decay to a very small value. I'm saying, let's say under 5%. And that way, when you bring it back, you're not going to be bringing back those motors out of phase. So that's the only reason I typically use time delay neutral switches, is where we have large motors.
Would there be a case when you would require arc flash reduction maintenance as well as GFI/GFP?
Okay, we're going to say that again. We have arc reduction.
Would there be a case when you would require arc flash reduction maintenance as well as GFI/GFP?
And ground. Okay, so arc flash reduction is any way of reducing the amount of arc flash that you get. And I assume when he said maintenance, we're probably talking about an arc flash maintenance switch. You need to have some arc flash reduction on all circuit breakers 1200 amps and over, or which can be adjusted to 1200 amps and over. And a maintenance switch is a way of having a short time delay on the switch, and yet you can turn the maintenance switch and get rid of that short time delay and have only instantaneous to get a lower number of calories, so you don't have to have an arc flash suit to work on the system. If we talk about GFI and GFP, GFP is ground fault protection. That means when you see a ground fault, you trip. GFI is ground fault indication. That means when you have a ground fault, you enunciate. You may have a light, you may have a horn, but you do not trip. So I don't know that I understand all the implications of the question, but in general, we don't use ground fault protection on generators. A ground fault protection trips. And let's say you have a building and it's on fire and the generator is running the elevator. Well, it's kind of ridiculous to trip that generator and not have any power when it's an emergency generator and you need it. Even if it's a non-emergency generator, then generally people don't want to trip on a ground fault. If the ground fault gets large enough that it trips the phase over current device, then you kind of got no choice. but generally we use only ground fault indication. And in the standards, in the National Electrical Code, there is no requirement for ground fault protection on the generator, only ground fault indication. In terms of the maintenance switch, I'm a big fan of those maintenance switches, and a maintenance switch reduces your calories and makes it safer. We have maintenance switches built into breakers that I described a minute ago. The generator manufacturers are also coming out with ground fault or arc flash reduction in their generator controllers, so that when you work on the generator, you can set the controller and tell you, hey, I'm working on this generator energized, and they've got arc flash reduction maintenance built into the controller that will trip quickly in the event of a fault and lower the amount of calories, and thus reduce the danger of you working on an energized generator. So I don't know if I answered that, but I gave it a shot, and that's kind of my opinion on it.
Can we use 4-pole for 3-pole switching?
Yeah, you can absolutely. If you need a 4-pole switch and you bought a 3-pole, you're in trouble. There is generally, you can't convert the 3-pole to the 4-pole, because by the time you pull out the whole mechanism and replace it, it's going to cost as much as a new switch. And so you want to make sure, if you need a 4-pole switch, that you buy one. Now, if you bought a 4-pole switch and you only needed 3-pole, no problem. You just don't use the 4th pole. So there's never a reason not to buy a 4-pole switch, other than it costs money. And of course, there's no reason to buy a 4-pole switch if you don't need it. But if you buy it and you find out, oops, I only needed a 3-pole switch, it's fine. There's no problem there. Now, you do need, in a 3-pole switch, a neutral bus bar, whereas in a 4-pole switch, you don't need a neutral bus bar. So it is possible in the switch you may need to add a bus bar to the switch in order to connect your neutral conductors. So it's really best to order what you're actually going to use. But you can't really go wrong with a 4-pole switch, but you may end up with some field work having to add that neutral bus bar.
What considerations are taken into account when a PV system is present on site?
So a PV system is a photovoltaic system, and this is almost a whole nother seminar, and so we won't get into it too much. Obviously, you need to make sure that you don't end up with out-of-phase conditions. Generally, PV systems are all designed to do that. You want to make sure that you do not feed power back into the generator, because if you push power into the generator, it's going to overspeed and trip. So you want to make sure that the PV system doesn't feed back. And again, PV manufacturers understand this, and they've already thought through these things and taken care of them. In many cases, on a PV system, you have a battery on the PV system, and you don't use your generator as long as the PV system has enough power in the battery to be able to supply your loads. And the only time you turn on a generator is when the battery runs low. And rather than parallel with the photovoltaic system, then all you do is have a battery charger, and the generator charges the battery. But there's a number of different layouts for PV systems, and I just don't have time to get into all of them there. I suggest you consult your PV manufacturer tell them you're using a standby generator, and they will all be able to tell you their recommendations for their system. Some do actually parallel, but a lot of them, for simplicity, they just have the generator charge the battery. So the PV and the generator aren't actually ever connected together.
All right, we've got a question that has a couple questions in it. I'll read through the whole thing and tell me if you need me to go back part by part. It says, is the 4-second neutral delay time based on spin down? If spin down time is greater than 4 seconds, will a longer neutral time be advised? How does that factor into the motor starter dropping out or staying latched in?
Okay, great questions. Number one, the 4 seconds has nothing to do with spin down time. If you have a motor and it continues spinning at full speed, that residual voltage in the motor is still going to decay. And so it has to do with the rate at which the residual voltage in the motor decays, and that is not based on spin down time. That voltage can decay to virtually zero, and the motor can continue to spin. What was the last part again, Tyler?
Yeah, so it said, how does that factor into motor starter dropping out or staying latched in?
Thank you. I'm sorry. I heard that and then I forgot that part. So the motor starter is going to fall out. And if you have your transfer switch, it goes to the neutral position, you lose power, the motor starter is going to fall out. And generally that's what you want, because you're going to wait. Once that motor starter falls out, if you looked on the motor side of the motor starter, you would see voltage starting at 100% voltage, and then it would be decaying down, and after 4 seconds, it would be less than 5 seconds. And then you're going to close that motor starter again in order to restart that motor. So it falls out.
Okay. What makes the fire pump rated transfer switch so different from a standard automatic transfer switch?
That's a wonderful question, and I probably should have mentioned that. First of all, Energy Management sells generators and we sell transfer switches. We do not sell fire pump transfer switches. The fire pump transfer switches have all kinds of codes and regulations that require them to be built different than a standard transfer switch. And one of the things is, on that transfer switch, if it fails, you may need to actually just hardcore connect the two together. They have ratings. The tests are different. And to be honest with you, I don't do fire pump transfer switches, so I don't know all of the differences. But I do know that we don't sell fire pump transfer switches. And when people buy a fire pump transfer switch, they always buy it as a package with the fire pump starter and the fire pump itself. And so I guess the simple answer there is there's an entirely different set of standards that go with fire pump transfer switches. They are much more rugged. They're painted red. And I don't know of all the detailed differences between them. They have to have the ability to withstand very high currents, because fire pumps have to be able to withstand locked rotor indefinitely. And so fire pump manufacturers are the ones that sell fire pump transfer switches.
Great. That looks like all the questions we had. So we want to thank everyone for joining us, and we look forward to seeing you next time.